Okie doke. Welcome everyone. Thanks for being here. So this is our topology seminar here at Purdue. Today we have Martin Tancer, who's visiting us virtually from Charles University in Prague. He's going to tell us about four manifold recognition problems. Thanks, Martin.
Thank you for introduction. So let me in the and thank you for the invitation. And let me try to explain what is the problem that I want to discuss. Let me start with the initial motivation, and this initial motivation is the homeomorphism problem. Uh, Basically, one of the most basic questions in the topology is like that: if we have two topological spaces, we would like to know whether they are homeomorphic. And I will restrict my class of topological spaces to manifolds in the beginning, because it's already interesting question for manifolds. And I want to regard this problem as an algorithmic question. So I assume that these manifolds are given by some finite input data. It can be, for example, a triangulation, provided they are triangulable. So this is what I want to discuss. And let me start with the very easy cases. So this is, of course, very trivial problem for one manifolds, which are just collections of circles. But it's also very easy problem for two manifolds, because we have a classification of surfaces. This is something that makes it easy. This problem is solvable for oriented three manifolds, but algorithmic complexity, if I at the moment, I'm only interested in the existence of an algorithm which may decide whether two manifolds are homeomorphic. But if I were interested also in algorithmic complexity, this is still like big open question, like what is the real complexity of this problem. Now let me skip the next natural case, which will be actually the main contents of the talk. But let me skip to dimensions 5 and more. And basically, in dimensions 5 and more, everything is lost. Like it's known that already like the simplest possible manifold. Say if I talk about closed manifolds, the sphere SD, that it's undecidable whether some manifold on input is homeomorphic to the d-dimensional sphere. And so this is the case for d at least 5. And now let me explain a little bit more the missed case, d equal to 4. And in d equal to 4, we do not have a result at this moment saying that for sphere is a recognition of for sphere is undecidable, but we have some results for some other for manifolds. So there is a result of Markov from 60s, which says that there is a four manifold which is unrecognizable. And we can also be interested like which four manifold is it. So in a later work, I would say, but I am not completely sure. This is something that I deduce from other papers, but I was not able to read Markov's original paper in Russian. That it turned that this Markov manifold is a connected sum of S2 times S2 for some k. Let's say for the beginning that it's not specified which k is it. And then there is a work of Stanko, which focused on say on the particular k one may get, and and he proved that that actually connected sum of 14 copies of is unrecognizable. Then there is improvement by Gordon, like almost 20 years later, showing that actually it's sufficient to take 12 copies. I am going to talk about further improvement up to 9 copies, but of course the main point is not really like the concrete number, but it's really like the change in the method, like what are the changes when compared with the previous method. And if I say some keywords, then the approach that I propose, it avoids so-called Markov streak, which actually contributes to the complexity to this number that you can see, this number here. And I kind of hope that like with some improvement of the method that I present, it could be within reach to make it up to like just one copy of S2 times S2, which is like maybe the second most natural candidate, and this is something that's clearly out of reach for the previous approaches. Like I will try to comment on it a little bit later. So that's and I of course I already mentioned that, but if I want to talk about S4, I can in this notation I could even recognize it as 0 copies of S2 times S2, and this is like a widely open big problem for which maybe different people have different opinions whether it's recognizable or not. In order to say at least something about the proof, I need to show. I need to start with talking about group presentations. So I assume that for this audience, it's something very well known, but just let me go quickly through it so that we are on the same page. So I have some finite group presentation. I have some number of generators. I have some number of relations. And instead of formal definition, let me give an example. For example, I may have generator 2 letters A, B, and I put some relations, basically saying that every relation is a trivial word. And if I take this example, then I present the group Z4, because like I have this relation A to the A times B to the power of -1, which is essentially equivalent to saying that A is equal to B. And then I plug this into the second relation, I get A to the 4 is equal to 1. And from this, it's easy to see that I have Z4. Usually it's not that easy. In general, it's a hard problem to determine from the presentation what is the underlying group. And let me mention one more definition that I will often work with, and it's the deficiency of the presentation. And for me, this will be number of relations minus number of generators. Some people have it vice versa, but I like to have the efficiency positive for the examples that I will be interested in. So this is simple example. And if I talk about group presentations, like basically the main tool for any undecidability result in topology are undecidability results for in algebra, and more specifically for group presentations. So I will need the following two problems. The first one is the triviality problem. This is the question if I am given a presentation, whether it actually presents a trivial group. And even if you ask this simple question, then this is algorithmically undecidable. And the second problem is so-called word problem. This time we have the presentation is not an input, but the presentation is fixed, and we have a word on input in the given alphabet, which possibly like with powers, positive or negative powers, and we would like to know whether that word is trivial in the presentation. And this is again algorithmically undecidable. At the moment, I will not comment on how to prove this, but later in the talk there will be some fragments of the proofs of these two results. And just for the word problem, I have here an example, like I have the presentation that I had before, and I may ask whether this word a square b cubed times a to the power of -1, whether it's trivial. And in this case, it's again easy because I can rewrite the word in this way that I plug a here and I plug up and I put one more a to the power of -1. This one is trivial because of this relation. I get this one, which is a trivial word. So this is just example like what might be an input of this problem. And let me mention like this is again kind of like perhaps the first basic consequence in the topology, the following corollary of the triviality problem, that it's undecidable to recognize whether a given two-dimensional complex is simply connected. And this complex, it might be a CW complex or it might be simplicial complex, depending how one wants to represent the input. But let me just show basically the proof of this corollary. And the proof of this corollary is one can take like space with a single vertex, or say CW complex with a single vertex. Then for every generator which I have in the presentation, I put there an oriented loop, a directed loop is there. And then for every relation, I put a disk, I glue to the loops a disk with the boundary corresponding to the word that I see here. And if I see power to the -1, then I go in the opposite direction. So this one is a b to the power of -1. Here, this is b cubed times a. And this is basically introductory class on fundamental group, that the fundamental group of this complex is exactly the same as group presented by the presentation. So in other words, the fundamental group of this complex is trivial if and only if my presentation presents a trivial group. I have included this this construction because I will need it also later on. But now let me go more into the topology and into the original problem. And now let me try to describe Markov's original method in general. So let me recall that our aim is to show that if we are given a manifold on the input, it's undecidable whether this manifold is homeomorphic to this connected sum of copies of, say, S2 times S2 for some number k. And the first step is algebraic, or it's on the boundary of like say algebra, and computational like foundations of computer science, computability. And this is a construction of a set or a sequence of presentations, P1, P2, and so on, which have I have another like additional requirement that they have some fixed number of M relations. Like so this I really want to have a fix, and I want to know that the triviality problem is undecidable for this sequence. So this is a stronger statement than the previous one, that the triviality problem is undecidable in general. Now I need an addition that the number of relations is fixed. The second step is, on the other hand, purely topological, and this is a construction of certain five manifold, and from a given presentation, I want to construct a five manifold such that the fundamental group, but not of the manifold, but of the boundary of the manifold, is isomorphic with the group presented by the presentation. I hope that you don't mind this small abuse of the notation. If I write here isomorphic with B, I really mean group of the underlying presentation. And the third step is so-called Markov streak. It's it's a step that adds some additional handles to this fourth manifold, meaning to the boundary of MP. And after adding a sufficient number of handles, we can get a manifold such that it's isomorphic to the connected copy of K S2 times S2 if and only if the original group was trivial. So it's some kind of stabilization procedure that adding these handles makes it easier to determine which manifold do we have. And it's sufficient to use the number of handles such that the final K is the number of relations. This is step number 3. This is something that I eventually want to avoid.
Can I clarify, Martin? So you're adding 5-dimensional handles onto the boundary of MP. Is that right?
No. It's 4-dimensional. Yeah, it's definitely 4-dimensional handles, and I would have to recall whether these are. I think those are 2 handles, but I would have to recall that whether I'm saying it correctly.
Okay, thanks. No problem.
So the result is always a 4-manifold. Okay, so that's the rough structure of the proof. And now I want to mention what are the differences, what one can do slightly better. And for this, let me mention it as a theorem. So the theorem is that if we have Adian-Rabin set, but this time not with the fixed number of relations, but with fixed deficiency, then we actually can deduce that the connected sum of K copies of S2 times S2 is unrecognizable. So the parameter this time is just the deficiency of the presentation, not the number of relations. And it's much more realistic to get smaller deficiency than a really small number of relations. And in particular, like when I had the first theorem, I tried to see how much can I optimize the deficiency? So I made it up to 9. And let me just compare it with the previous work. So the previous work was related to number of relations. So Gordon constructed a number of Adian-Rabin set with 14 relations, and I can also mention that in these constructions it's also always the case that the number of generators is 2. Actually the deficiency of this set would be 12. But with the results only on the number of relations, this is the basis of this Stankos 14 copies. And then there was another improvement by Gordon in 22, who this time constructed the Adian-Rabin set with 13 relations, and he has shown how to save one handle in Markov streak. So this was giving this 12. Okay. Okay. So this is some comparison, and now let me try to gradually describe some ideas for the first theorem and then for the second one.
Can I ask a clarifying question? So
Yes.
in your step 1, why do you need a whole sequence of presentations instead of just like what if you take a constant sequence of presentations? Do you need the sequence of presentation to be different in some sense?
This is it's important that actually in the construction the presentation is on the input. So if I have only one presentation, it's not saying much. Like I really have to be able to submit the presentation as input for the algorithm. So if I had only one, I would be able in advance to pre-code whether the answer is yes or no. But if I have a sequence, then the point is that I don't have an algorithm that answers yes or no for all presentations.
I see. I see.
He's like really reducing from the triviality problem for the entire group, not for like the word problem inside of one group, for example.
Yes.
I see. Yeah,
It's
thanks.
like triviality problem for.
Okay.
Okay, so let me first try to explain this first theorem that actually it's sufficient to use deficiency, and for this I describe the steps that I mentioned in more detail. So for this, let me actually start with something that I called step 2, which is construction of the manifold. And the construction of the manifold, let me mention the proposition that I need, that if I have a group presentation, then I can construct a 5-dimensional manifold, which with some properties. One property is that it smoothly embeds into R5. The second property is this key property that the fundamental group of the boundary is isomorphic with the group of the presentation. And the third property, it's something relatively easy to count. I can also count the dimension of the second homology, or like I can say that this is isomorphic with z to the power of 2k, where k is the deficiency. This is and let me just very briefly sketch the construction. This is actually not very difficult because some previous slides I have shown you a construction of 2 complex which has the same fundamental group as the group presented by the presentation. So I'm using 1-dimensional picture, but this is really a 2 complex in R5. I embed it into R5 by simply by general position, like taking general position linear embedding. This embeds into R5, and then basically I do something like a handle decomposition, but let me present it in the way that around the vertices I built some balls around the edges. Then I like the balls are 0 handles. Then around edges I built 1 handles. Then I may have some triangles. Then I would have 2 handles, but this doesn't fit that well into the picture. So this and I do everything in a smooth fashion. So then I really have a manifold smoothly embeddable in R5. I also have the fundamental group of the manifold is the same as the presentation because it, for example, collapses to the underlying complex. It's easy to check that this keeps homotopy type. And it's also not that difficult to check that actually the fundamental group of the boundary is isomorphic to the fundamental group of the manifold. And this third step, this I already said that also the computation of homology is not too difficult. This one I will skip. Okay. And once we have this position, then basically like if we have this Adian-Rabin sequence of group presentations, then our aim is only to show that we have this connected copy of S2 times S2 if and only if the presentation P, which is one of these one from this Adian-Rabin sequence, presents a trivial group. This is like what we need to show. And one implication is very easy because like we know what is the fundamental group. It is the group of the presentation. So if we have connected copy of S2 times S2, this is a simply connected manifold. So this group is really trivial. So the only task is to prove the other implication. And now we can forget about Adian-Rabin sequences. It's just a topological problem to prove like that under this construction, if we have a trivial group, then what we got is actually the connected sum of S2 times S2. Okay, so now I just recall what we want. So in other words, what we want is like that if this boundary of MP is simply connected, then it's a connected copy of S2 times S2. And now I am going to explain the tools. So the main tools is somehow suitably employ intersection form on fourth manifolds. I just use this very simple slide for intersection forms on surfaces. This is against standard, so I assume that most of the audience knows this, but let me just briefly go through it. So if we have an orientable surface, we can look into the base of the homology. So for example, for this double torus, I have base of the first homology given by the circles that you can see here. And then I have a bilinear, antisymmetric bilinear form, which is which corresponds, say, to oriented intersection of these homology classes. For example, 1 meets 2. Then depending on the orientation, I am getting here 1 or -1, but 1 doesn't meet 3. So then I am getting a 0. So altogether, this intersection form is given by this matrix, or you can also see it as like the direct product of those two matrices. On the other hand, if you have orientable surface, then actually the intersection form Okay, so here I'm cheating a little bit because this I have to do over Z2, but it's basically a diagonal matrix.
So those are cross caps, just to clarify. Those are cross caps.
These are cross caps. Yes, yes, these are cross caps. And I want to mention something, the same thing for manifolds. So for the moment, let's just very briefly give me some comparison. Like if we talk about surfaces, basically we have counterpart simply connected for manifolds, like closed simply connected for manifolds. Like counterpart of S2 is says S4. If we take a copy of S1 times S1, then the counterpart is S2 times S2. We can make connected sums that I use. And it's also good to mention that in some sense, if I take surfaces, then I have real projective plane, and then the counterpart is complex projective plane. And I again make connected copies. Or I can also take complex projective plane with a different orientation. That's maybe one difference worth to mention, that complex projective plane is orientable, but it's not a big difference. And now, if I want to talk about intersection form for manifolds, they are completely analogous. It's some bilinear unimodular form, but this time they are symmetric. This somehow comes from the orientation considerations. And but actually, like the forms are essentially the same as case in the surfaces. For S2 times S2 connected sum of S2 times S2, I'm getting directed sum of those matrices, like anti-diagonal matrices. And for connected sum of CP2s, I'm actually getting a diagonal matrix. And the intersection forms really say a lot about manifolds, and this is or about closed simply connected manifolds, and this is due to theorem of Friedman, who proved that this is basically this basically implies four-dimensional Poincare conjecture. So this is this famous paper that if we have integral unimodular symmetric bilinear form, then we have at most one smooth closed simply connected manifold which realize this gamma S intersection form. He has more detailed theorem, but if I put these assumptions, that this is kind of corollary of Friedman's theorem. And there is also one more famous result about intersection forms, and it's that kind of describe whether a four manifold bounds and oriented five manifolds, and this is if and only if the signature of the form is 0. But from this other famous theorem, I will be using only the easier implication that if it bounds, then the signature is 0. And now I have all the tools to explain the say the final proof. So let me recapitulate what the proposition we had. So from a presentation, we are building a five manifold with the properties that I have mentioned earlier. And we aim that if we have a trivial presentation, then we are actually getting a copy of S2 times S2, so connected sum of copies of S2 times S2. And okay, so let's see what we have. We know that this boundary bounds a five manifold, and this five manifold is simply this MP, because it's a boundary of the five manifold. So we know that the signature is 0 by Rochlin's theorem. In general, intersection forms may be complicated, but if the signature is E0, they are pretty simple. there is classification of, or say partial classification of intersection forms going back to Serre. And in this specific case, these forms can be really only those that I have shown you, basically, like either connected sum of copies of this anti-diagonal matrix, or sorry, so direct sum, or direct sum of the matrices with 1 and -1, which like I have a diagonal matrix, and half of the entries is 1, half of the entries is -1. Those are the only two options that may happen for signature 0. But this is a lucky case, because we know for manifolds which have those forms. So by this Friedman's uniqueness theorem, we know that this manifold is either connected sum of copies of S2 times S2, or it's a connected sum of copies of CP2 connected sum with the same copy with opposite orientation.
Can I clarify here? So Friedman is telling us it's homeomorphic to one of these.
Homeomorphic, yes.
But is it not
So I am not determining it up to the diffeomorphism. I am only determining up to a homeomorphism.
Okay. Yeah, thanks.
And there is the very last step. And the very last step is that actually this connected sum of complex projective planes, it's impossible to get it, because they do not smoothly embed into R5 with whatever smooth structure. This is some little bit of computation with Stiefel-Whitney classes. So that's basically quite a detailed proof of the. Of course, I am skipping some details, but quite detailed proof of that first theorem.
Does Friedman's
Some
rule
question?
tell us, could we have a mixture of S2 cross S2s and CP2s and minus CP2s?
Okay. Mixture of S2 types, S2s and CP2s and minus CP2s is again a connected sum of CP2s and minus CP2s.
Oh, right. Okay. Yeah, it's one of these things I don't know very well, but okay. Yeah.
It's
like
basically
if I take, absorbs it. Yeah.
If I take the direct sum of this one with this one, then I am getting this one.
Okay.
It's like they're stably the same.
I see. Yeah.
In the sense of direct summing.
Yeah. It's similar. It's actually similar to surfaces. If I take unorientable surface and I add a handle, I am still getting an unorientable surface.
Sure. Yeah.
Okay. Let me check how much time do I have. I still. Okay, so
10 minutes.
I think I have about 10 minutes. So I will go more briefly through the second part, but it's also the intention, because this is basically only the fragments. So I just want to mention a little bit about construction of these Adian-Rabin sets, and I will see how far do I make it. So I just want to recall again what is the aim. We want say a sequence of group presentations with a fixed deficiency as small as possible, and we want to have this triviality problem undecidable for these group presentations. And what I claim is that there is Adian-Rabin set of deficiency 9. But again, what I can do is or what I can do now is maybe to sketch the construction of Adian-Rabin sets of fixed number of relations, and then maybe I will manage to indicate what are the changes. So for one of the possible approaches is like this. Result of Matisayevich which says that there is a semigroup with 2 letters and 3 relations for which the word problem is undecidable. So with this semigroup, what I essentially mean is like that I have alphabet. This time I use only words with positive powers, and what I am allowed is like to replace one word with another. And I would like to know whether two words are equivalent. So here is actually Matisayevich presentation. The 2 letters are say S1, S2, and the 3 relations are those that you see here. So this one with 5 and 3 letters, and so on. The only difficulty is like that if one wants to write it down, that the third one has 304 and 608 letters. And this
write it down in his
really
original
goes back
paper?
to computation of Turing machines. Like it's
Yeah. So sorry to interrupt, but did he write down these letters, L and M, explicitly? Just kind of say you can find them by this procedure.
This is difficulty because this is again something that I found in English or in some later paper, and I didn't manage to find these letters explicitly.
Okay.
These words. So here I am relying on that this result is correct.
Sure.
As well as all other results that I mentioned. There is then there is a theorem of Borisov who basically has shown how to build from this Matisayevich presentation a group with 5 generators and 12 relations for which the problem is undecidable. I can show what is actually the presentation basically, but it's not very illuminating. It requires to staring into it maybe a few hours, then one will start understanding what's going on. But I just displayed it, and it's actually not the final one. It requires some modification. This one has more relations. But then this is not yet the final task, because now I'm still talking about the word problem, and I want to have a sequence of presentations. And then there is this approach of Gordon and Miller to take a presentation with undecidable word problem, and if we take some word W, we can build a new presentation by adding some number of additional relations and 3 other letters. And the claim is that this resulting presentation, which depends on the word W, it appears exactly here, is trivial if and only if the original word was trivial in this presentation P. And it's maybe worth checking that one implication is really easy. If the word is trivial, then this disappears, and this beta is equal to 1. And once the beta is equal to 1, one can start plugging it into everywhere else. One realize that alpha and gamma is 1, and then every generator is 1. So this is actually not very hard to prove, this part, and this already gives this Adian-Rabin set. And now in the remaining 5 minutes, I will try to sketch the modifications with the fixed presentation, with a fixed deficiency, but it will not. It will be just fragments, and those fragments are like first, it's possible to actually reduce the number of relations by something called Borisov trick. Borisov's trick, and if you look into that previous presentation, you will find there are a lot of commutators with certain letter C. And what's actually possible to is to replace the words that appear here with the letters that appear here with some words more complicated, but only on two letters. And adding these relations AC is CA and BC is CB, so that they still remain commutators. This is so after this is done, this simply reduces the number of relations. And it's non-trivial to show that this works, but the idea is like that if it commutes here, then it will also commute here and vice versa. And in order to reduce the number of the deficiency, it turns out to be useful to modify the previous step here, and also like this approach to add some powers here and so on, and it yielded reduced redeficiency. And the most difficult part of the proof was to replace this Borisov trick with from some reason he used here some very specific words for which it was kind of easy to prove that this works well, but I needed kind of very different properties of these words. So basically it was necessary to rework this proof, and I just very briefly can show that like the tools that one can use here are again a bit topological, to use so-called Van Kampen diagrams to be able to say whether some word is trivial in a given presentation. Then one way how to say it is like to build a disk with the corresponding boundary label and to ask whether this can be filled with the corresponding relations. So in the case what we have here, this word is trivial because it can be filled with these types of commutators. And this somehow helps to translate one problem into another in this Borisov trick. And one kind of important property used in the proof is so-called small cancellation theory. And here maybe something that I can mention is so-called Greenlinger's lemma, that if we have relations that overlap in at most some fraction of their length, and we have a word filled with these relations, then actually for some of these relations, it has to big portion of the relation has to appear in the word. It's something like if you look at the boundary word of this Ri, then the big portion of it has to be part of also of this W, if they do not overlap much. And it actually helped to choose this Borisov encoding in the way that really the overlaps are not too large, and then I got required properties. So I apologize that these were only fragments, but I think it wouldn't make sense to go into more details. So that's it.
Cool. Thank you very much, Martin. It's very cool.
Thank you.
Do we have any questions from the audience? We've got at least one, but ask the audience. So maybe I'll stop the recording.